We're excited today to have Aslak Stubsgaard here from Copenhagen Atomics. But as I've been telling my group, you came all the way from Denmark, so the least you can do is come down from your office here and talk. He's the CTO and co-founder of Copenhagen Atomics, where they're doing work to develop a small molten salt reactor. And I think he'll tell us about it, but they're doing a lot of sort of real technology component development with near-term kind of opportunities to try and bootstrap it all to get to the final place. So with that, I'll let Aslak go ahead.
Yeah, thank you. And since I got in contact with Paul talking about software and OpenMC, I also threw a little bit of that stuff in there that it's like a small part of the company, but it's not something we normally talk about. But I thought there might be some people here today who actually could use that, or that there's possibility of collaboration. And yeah, so I put some slides together, and we can have a discussion afterwards, but you're also free to just interrupt and ask questions. So we can, both ways works, and then we'll just see how it goes from there. Copenhagen Atomics, we're a Danish startup that started like 6-7 years ago now. And we're like a group of engineers and scientists who got really inspired, a lot of it by the work that John did and the stuff we found online. And the thing that really inspired us was that this is something that we felt that we can actually, kind of throw together in the garage. Not a reactor, but all the technology that's needed to actually build a reactor. And that was what really sort of got us fired up, is that let's go and actually just try and build some of this and see what breaks and go from there. And that's of course it's a long journey from starting from that point into where we are today, but it's been really fun. But yeah, so I'll try and motivate a little bit, because the way that Copenhagen Atomics are viewing reactors and the type of reactors that we're developing, the base assumptions is maybe a little bit different than what people normally talk about reactors, but it informs a lot of the decisions that we have made and the type of designs that we're going for. So you've probably seen these type of slides before of energy use and where it comes from. Over the past 100 years, we've been steadily growing, and now it's shown in terawatts, and we're almost already rounding up on 20 terawatts, and most of that energy comes from coal, oil, and gas. If you look about through time, the distribution is not minimal, and so if we have to make something that drastically changes that distribution, we have to make something that really scales quickly, and so it's not it's a really difficult problem when you start to think about how do we in 10-20 years scale a fleet of reactors to levels of terawatts. So it's a completely different way you have to go about it than if you're developing domestic reactors for 5-10% of electricity capacity. Whereas we look at total energy, not just electricity, it's a huge job to do. And so I want to go through some basic back of the envelope calculations to sort of look at what type of reactors have the capability of scaling. And one of the sort of base information we need is just besides enriched uranium, how much fissile fuel is in existence. And from official IAEA numbers, there's 1,000 tons of weapons grade material. There's around 2,000 tons of plutonium still in spent fuel. And then there's around 500 tons already been separated. And most of that is done in the UK from Magnox fuel. So if we say, let's try and scale to a significant fraction of the world's energy using some of this, and let's say realistically, we probably can't start on weapons grade material. So let's just assume we can start with some of the already separated plutonium. How quickly can we scale? But you might say, well, why do we need to use any of this material? We can just run on enriched uranium. So I first want to show sort of a simple back of the envelope. If you take a specific design and then say how much burnup does you get out of the fuel, and how many years does it take you to discharge that fuel, and how much enrichment do you need for that particular fuel, you can sort of do a rough calculation of how much global enrichment capacity do we need to scale to 4 terawatts, because it's once through, you enrich the fuel, you run it in your reactor, and then you dump it. So I tried, and this is not to brag on any designs, we need all these things. I'm just looking purely at what can scale to terawatt levels. And the question here I'm showing, if you have enrichment capacity of any reactor design, and then sort of how much burnup you get out of fuel per year, then you can plot how many multiples of current enrichment capacity you need to deliver 4 terawatts. And you can sort of show the lines here, like, it's everywhere from like 10 times to like 1,000 times. And you can imagine not only the trouble of scaling, like to build thousands of reactors, if you now have to multiply global enrichment capacity also like by like 10 or even 100-fold, it's like a huge challenge on the enrichment side. But it can be done. It's not that it can't be done. It's just, do you want to take a chance of scaling enrichment, or do you want to pick another route? And for Copenhagen Atomics, we really focused on looking at breeder reactors, because we've like all the way from the New Piles Committee in like 44 in Chicago, they were looking at breeder reactors. They thought there was only like 20,000 tons of uranium. Like there's of course a lot more, but they were also like at a way lower energy production in like 44. And so the question is sort of the same, like how do we scale reactor fleets? So I did the same calculations here where you assume that you get some amount of initial plutonium to work with, and I assume like 5,000 tons, and you have infinite reactors, as many reactors as you want. Like how quickly can you take that fissile inventory and breed enough materials to start enough reactors to produce 4 terawatts? And then at the bottom you see sort of the reactor doubling time, and then the power to fissile inventory on the y-axis. And then this here is how many years do you need to actually reach 4 terawatts. And one of the interesting things we see here is that even with something like the molten salt breeder reactor from ONL, it's still a fairly long time frame. We're talking like 30 years. And that if there's no limitations on reactors, just starting with 500 tons. Maybe you can get a little bit more, but it'll probably take some time to actually just separate it out of all the spent fuel. And if I found, like, there's very few numbers publicly about this, but the one I found was for the molten salt fast breeder reactor, which is this European project. And there, the timeframes, you're down in like the 200 years. There was some big uncertainties on that data, of course. But that's to show that while fast reactors generally have better like conversion ratio, usually the fissile inventory is also like 10 times bigger. So when you're thinking about doubling times and how much material you need to build more reactors, they tend to be worse performing than a thermal breeder reactor, simply because you can make the specific power, so how many megawatts of power you get per kilogram of fissile material, that much smaller in a thermal design. So this is really what led Copenhagen Atomics to focus on how can we long-term get to breeder reactors. So we don't intend to start our first reactor as a breeder or even the first generation, but like the long-term goal for us has to be a thermal breeder reactor, because it's the only thing that we see is going to allow us to scale to terawatts without like vastly increasing enrichment capacity globally. So yeah, that sort of led us to a design which is something that has to be able to be mass manufactured and deployed. So it's the size of a 40-foot shipping container, and that's the fuel salt and the coolant salt. And it's without the shielding. The shielding is external to the container. And we view this as a model where basically the reactor is sort of the consumable and you reuse the fuel. And so initially we're hoping that one of these containers here can run for 5 years, and then you swap out the container and you fill in new fuel, or sorry, you move the fuel to a new reactor. And then these containers are basically just scrap after that. But the other thing we saw is that with graphite, you have a bunch of this graphite that you have to decommission, and the lifetime of the core tends to be set by the graphite, and then you can't do high power densities. So we had this thing that we wanted to switch to heavy water. And so the heavy water is unpressurized. So you have salt flowing at like 600 degrees in, up to 700 out. And then you have a small thermal barrier to heavy water that's the moderator. And you might think that you conduct a lot of heat, but it's actually minimal. The vast majority of the heat is just from moderating the neutrons. So you lose like instantly there, like a couple of % of your total reactor power on just, heat that you dump, because it's like unpressurized water. You can't do anything with that heat. So we have outside of the core, we have like basically a commercial air conditioning unit that we cool the water with. And what this allows is a better neutron economy than graphite, and you can reuse the moderator. So similar to the fuel, the moderator is swapped from reactor to reactor, and we are left with like a husk of stainless steel. And they don't cost a lot to build, these husks. Like it's a lot of welds and a few pumps and a heat exchangers, but it's not that bad actually. The fuel production is like a way bigger capex than just the reactor. So the fuel we're using is enriched lithium 7 thorium tetrafluoride plutonium trifluoride as a starting fuel, and it's just like 1 to 2 mol% of plutonium, and the eutectic is like at 3 mol%. So there's still like a fair margin there. And then as we burn the plutonium, we build up uranium. In the beginning, it's not going to be a breeder, so like conversion ratio below 1, but we're still going to produce some uranium-33. And we have a blanket around that core, and that's also much sort to act as a radiation barrier and capture some of those stray neutrons. So we can actually build a core in this size, like a normal shipping container is like 2.3 meters in width. So we can build a core with a size, and by using a blanket, we can get like neutron leakage down to like 1 to 3%. So you can get super efficient in a really small size because you have a blanket. If you don't have the blanket, you lose like 10 to 20% neutrons. Unpressurized, and we want to do this thing where it doesn't have to be a breeder in the beginning. We just need some fuel to kickstart it. And then over time, we want to improve the design, and we want to add reprocessing capability to turn it into a breeder. And we don't know if that's going to be like a 5-year, or 10-year, or 20-year process. We'll just, we'll first build one, get it to work, and then we'll take it from there. And some of the questions we had is like, can you do like protactinium or uranium separation inside a reactor, and is there proliferation risk associated with that? But our view, at least, is that all this is going to happen inside of a sealed container unit. And when you're there the first day and you load it with fuel, the IAEA is there, you close it up, and anything that goes on in there, it's completely closed system. You have no access from the outside. It only gets power in, and then it gets coolant salt, and then coolant water for the heavy water. And the system is completely autonomously controlled, and it doesn't download anything. Like there's no downlink, there's only an uplink of data. And the way you shut it off is just you cut the power, and then it goes into passive decay mode. And that's the nice thing about salts. You can like dump the salt to a tank where you have complete passive decay. And since we have a liquid fuel that we can dump and a heavy water moderator that we can dump, we have 2 independent ways of controlling reactivity. And there's actually some more things we can do there, but that leads us to say that we don't need a control rod. It's inherently safe, and there's multiple ways of controlling reactivity. So why build in mechanical control rods? So that's also a thing that we said early on, is like, we don't want to have control rods in this thing. And that's not unprecedented. The aqueous homogeneous reactor ran without control rods. Hey, question.
Yeah, I don't know if you touched on this later, but like, how difficult do you think it will be to license these?
That's a very good question. I'll get into this. So the way our company is set up is we're building these, first these loops that I'm going to show later, and then the reactors. And we want to build those and test them with fertile salt. And we want to test all that out and make sure it all works before we engage with the regulator. So we don't see a very good reason for us to talk to a regulator before we're completely sure about how it's going to work. And they have very little input they could realistically give on some of the things that might fail, because it's never the things you expect. You build these things and you have certain ideas of what is going to fail, and it's always some other stuff that fails. So we want, before we engage with the licensing process for a long period, we want to be very sure about our system and have high confidence that we've seen all the common failures and we've removed them, while it's still cheap to work with like simple salts in stainless steel before ever engaging that. So there's definitely some things here that we would like to do that probably like US regulators are going to be very skeptical about. But we definitely want to push back on that, because we believe that if we do it to some of these existing standards or beliefs, then it's going to be very hard to scale these reactors to many thousands of them running, especially like stuff like having a control room. It's going to make it super hard to scale this for like dozens or thousands of reactors. Yeah.
How are you controlling it without rods? Is it through the temperature or flow rate, the pump, something like that?
Yeah, so the core wants to have like an average density on the fuel salt. So when you pump up and down, you can basically, you'll tend to change both the inlet and outlet temperature around that average. And so we can both control the fuel salt flow rate and the coolant salt flow rate. There's like an intermediate basic fluoride coolant, and then a tertiary nitrate that goes out of the reactor. And then we can also control the heavy water flow rates and the coolant on that. So we can basically vary the density of the heavy water and the density of the fuel salt.
You have 4 flowing.
Yeah. So this thing is like, we joke that it's basically like buckets and pumps. It's like the reactor has like a hot part and a cold part, and then it has multiple circuits that are pumping around.
You have 4 heat transfer.
Yeah, so the primary one is, 2 heat exchangers inside the core from the primary heat. And then there's also a heat exchanger for the blanket. And then for the heavy water to the normal water, there's a heat exchange loop there. So it's a bunch of pumps and buckets.
Just a quick, so you said to shut it down, you just cut the cord. What does that mean?
That means if you cut power to the reactor, the pumps will stop and the salt will drain into the dump tanks where you get passive decay removal. So we also lose like a few percent of our power through just like passive decay removal.
So you just stop pumping.
Yeah. You were.
Yeah, so what's the operating temperature of the salt and why are you avoiding using beryllium?
So with any, you can, I don't know if you meant in the salt or as a moderator.
Flag.
Yeah, flag.
Salt.
Originally, we wanted to stay away from beryllium just because of the handling, but that's maybe less so a concern now. It's more so that if you use flag, you get low solubility of uranium and thorium, and you have no solubility of plutonium. It doesn't have a eutectic with plutonium. So you can dissolve it into it, but if your temperature drops, you'll plate out like solid plutonium trifluoride. And the lithium thorium, you can get a lot more thorium in there. So when you're trying to do the conversion, you actually want a bunch of thorium there. So it's like a tiny mass fraction of plutonium. And it has a higher melting point, but it's 550. We don't see it as a big concern. So yeah, that's why.
So from the way that's drawn, you've got a sort of blue thing coming out the left of the container, and is that going to the dump tank? And if so, does that mean you've got some sort of containment around this thing?
Yeah, so this schematic is from our initial concept back from like, I think 2016 or something. Now that actually dumps to a cold region inside the container. So we have a dividing wall where all the electronics and cold region is on one side, and then a hot region with like a furnace basically on the other side. So that dumps internally.
Right, okay.
And then, in case you have failure or breakage of anything in here, like some of the stuff can definitely boil. If we don't foresee it sort of, having any kind of explosion, it would actually take a few minutes to boil the water away. And there's like around 2 cubic meters of heavy water. And next to this, we have a condenser unit. So we basically have enough thermal mass to condense all the heavy water away.
Right, so you don't get a build up of pressure,
No.
steam pressure in there.
Exactly. So it's the outer containment outside the, like, I guess the third boundary is like thick containment that can handle pressure, but the container here and any of the tanks, none of those are pressure vessels. It's all super low pressure, basically ambient for everything.
Sorry, this last one. You mentioned a third boundary. Is that a boundary outside of that diagram?
No, this would be the third boundary. So you have like the salt tanks and tubing, you have the container, and then you have an outer containment.
Okay.
This is also acting as like a radiation biological shield.
Okay, got it.
Yeah.
Yeah.
And those things would tend to be like, you build these to last for like 80 years. It's just a reactor you swap out every 5 years in the beginning. Okay.
So I still wanted to hear what Prime Minister safe meant.
Oh yeah, this is like prime. Okay, yeah. So walkaway safe, we kind of cover like you should be able to basically cut the power or leave, and it should shut down by itself. Prime Minister safe is basically saying that no one within the authority should be able to operate it in any sort of undue manner or any malicious intent. So it should not be so that someone can show up on site and like, hey, you got to do this. Like the design should basically not allow you to do anything like that. And we're achieving that by just having it completely closed. I know probably someone could spend a week or a month drilling into the buckets. But yeah, that's sort of on the design basis. Yeah, so we have this timeline, and currently we're very hard building a non-fission prototype. So it's basically the full 100 megawatt is like a 40 feet container, and we're building a 1 megawatt demonstration reactor that's a 20 feet container, and we're building now a non-fission version of that. So we're planning to build several of them. The first year in the spring is just going to pump water, and in the fall it's going to pump FLINAC. And then next year we want to build an additional one to pump fertile salt, so just lithium thorium eutectic. And so a lot of our time now is just spent on ordering all the components. Most of the tanks and containers have been ordered, but we still have to produce like something like 12 tons of FLINAC this year for this setup. So from some of the other loops I'm going to show you that has like 50 kilos or like 40 kilos, it's like a huge scale up in the amount of actual liquid you have in these systems. So that's what we're really hard at working. But we don't need any approvals for any of this. This is like, we're building loops, that's just it. And we want to see these work like perpetually for a long time before we go on to approval. We have a huge lab space at Alfa Laval. They used to have a decanter production that they closed down, and we were able to basically just rent out a huge factory floor. And then we also have a bunch of office space there. So that the previous photo is a little bit older one. This is still like some of these slides I have from my ONL presentation in October. So sorry if some of you've already seen these, but basically we have like welding stations and lathes, and we also got a laser welder, and we have like a pump lab here in the back. And then we have a bunch of loops. And yeah, that's where we do most of our manufacturing. We're roughly a little bit more than 50 people right now, and we hope to hire an additional 50 before the end of the year. So yeah, if you know someone, or if you want to move to Copenhagen and play with salts, it's always an open offer for anyone to apply. We're very happy about the fact that all these systems we're running concurrently. I wrote Thomas yesterday and asked what the number was. Currently it's 34 years of accumulated testing on these salt systems. And it's around 4 years per month additional time we get on that. And some of them are pumping, and some of them is just static salt systems, but it's because we have like Raspberry Pis running on each of these systems, uploading to a cloud server, so we actually get real time how much accumulated times they've been running. And we want to get this to like, hundreds of years before we build a reactor, even maybe thousands. So we need like a lot of just experience and testing time to have confidence that you want to start any of these things as a reactor. And the workhorse of our work is these loops. We built many different types of designs in the beginning, but we got really settled and happy with this design we have now, where it's basically based on a Euro pallet. So the bottom, this is like the dimensions of the Euro pallet. And the idea was that we should be able to like roll it through a door and get it into any lab. And the way it's set up is that we have inert containment on the whole outer walls here. And then we have a furnace region with insulation and heating elements protruding inside. And then we have an electronics box with all the valves for the gas and data acquisition and fuse box and all the things we need to run the loop. And the reason we did this is because originally we had sort of a furnace, and then we have a bunch of penetrations into the furnace, and we wanted inert gas on the outside, and getting all those penetrations to be leak tight was like a hell. So like, let's just move all the electronics next to the furnace instead. So that's what bore this design. And then we added an air conditioner on top just to keep that region out here cold. And then we have like penetrations out the bottom for like power and gas in and out. And sometimes we like route some instrumentation. If we are testing something new, we just route it through those front ports. And then we can just we have holes here, or we can drill additional holes into the furnace region, and without having any gas tightness around that, we can just shove stuff in the furnace. And then we started adding like glove box ports to the front because we wanted to go in there and fix something while it's running. So that's what those holes are. Is normally we actually can go in there and fiddle with it. And then we have some other penetrations at the top here, and then here is a stop button with a Raspberry Pi that's uploading all the data that we get from our electronics to a web server where we can go in and like view the data and like view pump speeds and like pressures and temperatures. All the data is just streamed to one server. And yeah, I just brought some different pictures of the sort of the lab space. So here you see one of these loops, and all this electronics is all stuff we develop ourselves, both the software and the electronics. Yeah, so it's just like it takes like a roughly 22 kilowatts of power, depending, like it can run on different voltages, and then gas in, and then it has two gas outlets, one for the copper gas on the outside and one for the salt wetted system. Yeah, and then if we look inside, this is sort of one of the setups where inside we just have a tank at the bottom with the salt, and that can hold up to like 25, 30 liters, but we normally just have like around 20 liters to sometimes as low as like 10 liters of FLINAC in there. And we can do other stuff. We've done like nitrate salt. We haven't done a lot else than those, like just because we haven't had a need. But in principle, you could pump a lot of different things around here. And then we have our own pump that we developed ourselves. So when we started, we looked around for different pumps to test with, and we couldn't find anything. And the ones we found were like exorbitantly expensive. So we said, like, how difficult can it be? And it turned out it was like super difficult, but we decided, let's just build our own. And we also decided very early on that it should be a canned pump, because we thought that to get a reactor approved, it would be very difficult with a cantilever type pump with a shaft and everything and a seal. And we also saw like the ORNL data, and like that oil ingress seemed like a nasty thing. And then on top of that, because we're designing these to not have any maintenance, we're like, let's just put it inside the furnace and have it hermetically sealed and be done with it. And that actually, so we thought making the stators would be like the difficult things. And it actually turns out that getting the bearings to be salt wetted and run for like months was the difficult thing, and not the stator. So to my knowledge, it's still the only pump that runs at like 700 C, like with the motor inside the salt. But yeah, so we have wires going through for like thermocouples and sensors, like leak detection sensors and gas. And then we put a little pressure up to prime the pump. And then we start the pump, then we pump it basically around in a loop. So hence the name, it's just pumping around. And usually we pump these with like 250 liters per minute. So that's like, and sometimes up to 300. So that would be like 80 gallons per minute. I'm not good at imperial, but yeah. So it's just going at it in there and pumping around. And it's going through like a flow meter. There's a filter here, and then a valve, and then it's going back. And so it's just completing that circuit. And then we've built other systems where we do a bunch of different things, but this is sort of our base system. And normally we like the purpose of these, it's not like we don't do corrosion studies a lot, and we don't do like thermal hydraulics validation. We just want to see them run, like, and see what breaks and then fix those things. So it's much sort of just, run the system to failure and then improve on it, and not so like academic studies. And I included like a picture here where like in the lab, often we're like repurposing these systems like maybe once a week or once every other week. So like you want to test, you take stuff out, you put in some other things, and someone has a project where they want to test the component. And so a lot of this is just putting new stuff in. And I think this one here is like 2 tanks on top of each other. I think I have another picture of it, but that's just for filtration. So we can load in salt in a top tank, and then we can either do refinement or just pump it through a filter to another tank. Also, if some component craps out and you get like stuff in the salt, you want to refilter it to start a new test. Yeah, so this is one of these other systems where it's just doing like filtration. And one of the things we have is inside the furnace, we put in like steel plates, like as a splash guard, because if something breaks or the flange goes off and the pump starts empties all the volume in there in like a few seconds, we don't want that to all go in the insulation. So we have just a splash guard and a bucket at the bottom. So even though this never happened, in principle, it would deflect it all to the bottom without getting into insulation, because there's inert gas on the outside. So whenever we've had a small leak on a flange or something, we just open up and we can like scrape the salt off. There's no corrosion really, and we can just like run again, basically. Change the gasket and then rerun.
Is that the nitrate salt or FLINAC?
Which one?
The ones you're talking about. Which salt is
For both.
for both?
Yeah. Nitrate salts tends to have like a bunch of dirt in them, FLiNac salt less so, but sometimes from the purification process, you get like either like small metallic particles or corrosion products that you want to sort of remove through a filter. So in general, we want to start with like a pretty pure salt. And
you're doing the hydrofluorination.
We're doing a bunch of different things and trying to validate which is sort of easiest to scale up, but not so much hydrofluorination, I think, on a bigger scale. But in general, we do CV analysis to figure out the oxide concentration in the salt, and we try to get this to like below 50 ppm, but it's taken several years to get to this point, and we can run these loops with like higher level impurity. It's just like what is going to fail first. But yeah, we generally like we like to see that when we filter the salt, it's like completely white, and like you can see the crystal structure in the salt, and like yeah, if it's completely white, then it's a good sign. And here we also had to make we didn't have to, but we chose to make our own flanges based on like triclam flanges from the dairy industry. And that was in part because you can buy so many components to modify with triclams on them. And we found by just putting in a graphite gaskets, they were fairly like good enough. But we then modified them a little bit so that we get a little bit better leak tightness. And then we also put on like a bigger clamp to just not put too much torque on the bolts so they don't gall, but still get enough compression to make it leak tight. And on the other picture is like a look inside our pump impeller after it's been pumping with FLiNac. Yeah, we don't show too much of what is inside that, but I guess that's a little peek view. We also developed like a turbine flow meter, seen there on the left on I guess your side. And that's just, a small impeller spinning around, and then we made our own high temperature sensor to just pick up the electromagnetic field from that small turbine wheel and measure the flow rate. And it's kind of, it's a coarse measurement. We don't have like a good calibration of it, but we mostly just use it to see that we're primed and we're pumping well, and there's like stability in the flow. And then we're also using Alfa Laval's alfanova plate heat exchangers. So to our knowledge, Alfa Laval is the only one that makes plate heat exchangers where the bracing compound is stainless steel and not like a stainless steel alloy or copper braced. And that's of course super nice because that you can potentially use in a reactor. These things are made for like 30 bars. We have like a quarter of a bar pressure drop across the heat exchanger or something like that. So even though they've not been rated for nuclear, this is one of the things that we want to try and get approved for molten salt use. And the whole idea is if we can minimize the fuel salt volume outside the core and the heat exchangers, that plot I showed you earlier of how quickly you can scale to terawatts, it has a huge impact because the majority of our salt in our system is outside the core. So if you cut that down by 50%, you just made your reactor like way better. And so just, heat exchanger salt volume is like for us a way bigger parameter than some other like neutronics factors. So like this is sort of the stuff we want to optimize. But the only commercial product we can see right now that seems to be well suited is like these plate heat exchangers. And when I got a tour earlier today, I saw some different heat exchanger designs that could be very interesting to also implement in the future to actually get more performance out of the same core. But we're using these, and they've been working very well. So one of the things that I have a slide on later is like actually being able to model the heat transfer flow in these is actually a surprisingly annoying problem. And so we don't know how many of the biggest models they have the biggest model is like 0.5 meter tall, and you can get them like 1 meter deep with plates, and we don't know if we need like 1, 2, or 3 of those. And they each have 100 liters, so that's a huge impact because our total salt volume, if we have like 2 to 3, is like 400 liters. So if we can remove one of those, that would be a huge impact on our like the economy of our reactors. Then we made our own bellow valve. So again, hermetically sealed and then just pneumatically actuated. And it's it's one of the things that like was kind of surprisingly easy. Like it worked the first time, and then we haven't changed it. There's some gas systems over there that's mainly also using like triclamps. Yeah, we bought a laser welder to just weld a bunch of these things. And laser welders have gotten pretty cheap now. So I would like recommend your lab also like look into buying one of these, because there's a bunch of things that you can do with a laser welder that you can get really nice weld. And you don't get a lot of distortion when you heat things up, because if you TIG weld things together and you heat it up to 600, it just bends in every direction. And you don't get that with a laser welder because you get such a small heating zone. So you can do a bunch of cool things. And then we're also starting to test for, we have the static salt test system. We're testing silicon carbide carbon composites and carbon composites. And this is sort of, we don't want to build the first reactors with these materials, but we want to learn more about how they work and if it's something that you could use in a reactor core for piping. So these have flanges at either end, and then we're putting our standard flanges on that, and we're filling it with salt, and we're doing like thermal cycling and pressure cycling to just see after like a month or a year, like what does it look like. But from a corrosion standpoint and from a neutronics, like material embrittlement standpoint, they should be better, but remains to be seen how the manufacturing is on this and whether you can get it good enough. Then again, when we started, like we couldn't find any salts. So we did the same thing like probably everyone else like kind of do, and like buy standard salts and try to run with them and have to like go through the purification of the moisture and oxides and metal impurities. And we spent a bunch of time, but it's not like it's still like a smaller part of our company, but like spent a bunch of time actually just figuring out how to make clean salts, and then how do we scale that to actually produce. Like now we're like at 100 kilos per week max capacity, and we want to be at like a ton per week in like a few months. So we're building a bunch of new systems to just scale the production higher. And now we've been doing it in like small glove box samples for like corrosion testing, and then, but we don't do a lot of corrosion testing really. So it was more just to play around with it. But most of the production we do is in like ingot form, and we load those in these buckets in the loops, and then we run with that. But now we're sort of looking to do it in like bigger flasks and do like, like 20 to 50 liters per batch, and then just having like 30 of these system runnings in parallel. And then all the electronics and software, we have like a couple of people just doing software and a couple of people just doing electronics. And we do it like it's all in-house done. And that also allows us to practice basically making these autonomous reactors. Like, we should have like half a decade or a decade of experience in building autonomous systems before we try and do that with a reactor. So the loops are all autonomously operated. So we have like program sequence from everything from like purging the loop when you start, to heating it up, to automatically priming at a certain temperature, run for an amount of time, throttle up and down like RPM on the VFD, and then deprime and then cool down. And that's the same kind of operations you want to do in a reactor. And so like for thermocouples, we did our own sort of board. For actuating valves and actuating heaters, we did our own boards. And then all these have just like small ARM microprocessors inside, and they communicate with a Raspberry Pi that sort of does the control mechanism, and the small boards are just doing actuation. And in a reactor, we want to do multiple redundancies, both on sensors, on the actuation boards, and on the control system. So that we're implementing that now in loops, that we have like 5 to 10 Raspberry Pis, and they're all doing consensus control on the loop operation. And they're all uploading to a data, so it's only an uplink, there's no downlink. And if one of these falls out of consensus, the other one continue working. And if one of them falls out uploading data, they can buffer for a while and then upload when they get connection back. There's also an uninterruptible power supply that basically allows it to keep uploading data and actuating control. So if the building power goes out, the loop keeps operating, but the pump shuts off because it draws too much power. But all the controls keeps operating for like several hours. And when power comes back on, it dumps all the data that it acquired in that period to the cloud server and keeps running. So yeah, that's been like a great asset to actually do all this, because like we'll have to do it anyways for a reactor. Like we can't apply be contingent upon a bunch of third-party providers to do all these weird systems that have to work together. It has to be like very succinct and like integrated system. And then we do also these static salt tests in tubes, and that's mostly just to test our gaskets, actually, not so much corrosion. So we have a tube, I guess I can show it in this one here. We have a tube with a flange at the bottom, and then a heating element, and then we have inert gas on the inside of the tube and on the outside. And then we just put a slug of salt in there, and then we do temperature cycling and pressure cycling on the tube, just to see like the stresses and like whether it leaks after like a week, a month, or a year. And we started some of these to do like a year-run test here on the left. That's, you know, it's corded off in our labs, and like, don't touch this. We want to see if it can run for a year. But most of these, we run them for like, you know, a weeks or a month at a time. And it's just sort of, yeah, all of them do the same sort of control with a Raspberry Pi to a server. So that's how we're getting all that data on like on our systems and all those years of runtime. Yeah, and then I want to go into a little bit sort of a different realm of what the company is working on, which is like all this other stuff is the majority of the company, and then we have a small group working on supporting open source software development for molten salt reactors, but in principle also molten salt cooled reactors or like fusion salt cooled reactors, anything like where you have a fluid you want to model with neutronics. And for Copenhagen Atomics, we really strongly believe that it's very beneficial to the industry if we all use the same open source code and develop on that, so that there's going to be like cross verification instead of every company working on their own closed source thing. So we want to try and support, even though it's not like the major goal of our company, we want to try and support as much as possible open source development for these different purposes. And for us, it all has to be like CAD based. Like at least for Copenhagen Atomics, we want to move everything to just running on CAD models. And we want to do like neutronics, and we want to do like radiation models of the whole reactor, and also radiation, like heating from gammas. We want to move also into like coupling neutronics, but it's not something we find is like super present. Like it's not what's holding us back now, that we don't have like the greatest coupling codes for like multiphysics. But it is something that the industry needs, I think, to develop over time. Similar with transient models, it could be like short term where it's coupled to like multiphysics, or it could be like longer, like hours term scale where you're doing like separate models. And depletion, that's something that we're really interested in, because we're actually thinking about how do we bring a fleet of thousands of reactors to like a fleet of thousands of breeder reactors. So the depletion side is something we're really interested in. And then finally, like heat exchanger modeling to actually know how many we need before we have to build like a giant setup to just measure it, which we might just end up doing anyways. And what we're doing now is we've developed CAD files for all the MSRE reactors that were built. Have a few pictures of them. And some of them we've already made open source, but we're making all this open source. And the idea there is that we have actually 3 reactors that were built at ONL through the 50s to 70s. And those are like great benchmark cases. Oh, even though some of the data is kind of like, you know, like some, you know, you might have a drawing that's just a conceptual drawing and you don't know if it's actually what they built, but still, like you can get a lot of details there where you can actually try and do some validation to know, like, are you like within like 20% or like 50%? Like what's your uncertainty on your calculation? So we have like a full model of the aircraft reactor experiment that used like a beryllium oxide reflector. They wanted to use like solid fuel originally for the aircraft reactors. And so they bought the moderators because the production time was so long on them. So they bought that, and then they were worried about in the documents like spaghetti-like fuel. So they switched over to molten salt, but they still got this moderator. So this core design is basically because they already had the moderator. So they just pipe, you know, in Inconel tubes, they just pipe the fuel salt through it. But yeah, kind of intricate design, but we're able, with some help from the OpenMC and DAGMC community, to get these models up and running. And they're actually, even though it's like hundreds of step files, it's running pretty smoothly. And then there was this lesser known, we call it zero power reactor experiment. It didn't really have an official name, so that's just what we're calling it. And it was a beryllium metal reflected moderated molten salt system. And they had basically a bucket of fuel salt at the bottom, and they pressurized into this annulus between like beryllium on either side and brought that critical as a zero power experiment. And they had all these like gold foil stacks inside to try and measure flux densities. So we just put all the information into this CAD file. And we're currently running this now, so I don't actually have any export pictures of the criticality. But like we just dump all the details in there, every tiny hole and nook and cranny and thing we can find in a document that was there, we'll put all of it in there. And the hope is that by using these different, well, I guess also there's the MSRE, and it's the same story, like all the details in there. It's like a complete, almost engineering level CAD file of the reactor, and yeah, it runs great. So that like we're super happy about that. That there's actually an open source modeling tool out there that's capable of this. One of the things is that the meshing tool is still like a licensed thing, so we would like to see an open source alternative, and we're actually developing on is actually making a path to do the meshing open source as well. But yeah, we can like pull control rods in and out and see the effects. So we do it all in CAD, and then we model it. And also we try to do some validations on the shielding, and there the information is more sparse about like the dimensions of the thermal shield and the material properties. So we had to do some digging there, but it still works like surprisingly well. And then for the heat exchangers, we also had a master project where we did full CAD models of the primary and secondary heat exchanger and did like full CFD heat transfer on the heat exchangers. And the heat transfer like gave like spot on data, but the pressure drops were like way off. And the problem is also that we found out they never measured the pressure drop. They inferred it from calculation, and they measured on the water setup. So we don't have good data to validate pressure drops. And we get like very different readings, which is also sometimes like CFD can be a little bit fiddly with pressure drops. And same for this was the coolant to air heat rejection system. So this is one of the big questions for us is like, how much pressure drop do we have in these alfanova heat exchangers? And we did a model of one of the smaller ones that we have in our loops. So the hope is that we can actually do some validation there. We would in principle not like to do this sort of stuff, this like more research kind of, we just want to build stuff and break it. But in this case here, it's actually pretty crucial for us how much the pressure drop is and how much fuel, like how many of these heat exchangers are we going to need. So we're trying to use the ORNL data as sort of a benchmark for just thermal hydraulics of heat exchangers. And these models are also open source, so that's also something you can like download and play with. But yeah, that's it.
Any questions?
So you mentioned that the running things and breaking them and iterating like this was your kind of way of moving forward, right? So roughly, what are the causes of breaking that you have noticed the most in your systems, or is it a little bit all over the place?
Yeah, it's kind of all over the place, and with a certain component, it's all weird kind of feel, and then you remove some of those, and then you see a more consistent one, and then you can actually go and design for like removing that one failure, whether it be like a tolerance or like stuff warping, like those are things we've seen a lot. Yeah, but also on electronics, like there'll be like a new board update for like a heater or something, and then you find a bug, and then you have to go and order a new board. So it's like it's not just on the like salt-wetted hardware side; it's also a lot of the integration between the control software, the electronics, and the hardware, like how that all works together.
Okay, and so within your components, are the pumps the most challenging, or is it maybe the heat exchanger?
No, so the pump has been like, especially like the bearings on the pump has been a big issue for us to get that super reliable. And we're developing the same version of the pump, but with electromagnetic bearings. And we're actually planning to have that up and running here in the next half years with salt. And the hope there is that can actually run much longer because you don't have any wearing surfaces. But I still think that will need a lot of time to just mature to be a stable product that we can actually put in a reactor. But yeah, definitely like a lot of stuff has been on like integration of everything, or like something goes down over the night and you have to come in the morning and fix it. So, and then also on the pump, we've had a bunch of stuff, but actually the whole motor part of the pump has been surprisingly well behaved. So it's mostly on the bearings because they're salt lubricated.
What's the CAD system you're using?
We use Onshape. I don't know if people here are familiar with it. It's we like it a lot because it's a thing that we can also recommend to like students and external people, because you can get like a free hobby license, and there's also a free academic one, and it's super professional. You get most of the features you get in traditional CAD, but it's version controlled, so you can like collaborate multiple people together, and you can like merge features in CAD. So that's super cool. So that's and you can also couple it. There's like something called SimScale, like a CFD tool. It also has heat transport that couples to Onshape, so you can just import your files and run like a CFD case on it. So that's pretty neat. Nice little added feature.
So I'm not sure if I understand right. It seems like the only thing we can do with that reactor is that you should shut off the power if you want to do anything. Is there any other thing you can do to interfere the operation at all?
Yeah, that's, some of the things I could worry about is like, is there a way to like spoof the software by, sending oscillating like hot and cold salt in, or like, is there, that's some of the things where you could have like weird bugs that you have to pan out if there's some way to like spoof the control mechanism. But you want to have like long response times so that it's sort of more plain. I guess you could like, go there and drill into it somehow, or, try and turn it upside down or something weird like that. But you probably need like a pretty good crane, but the heat rejection system is dependent upon the salt draining to the bottom. So if you somehow manage to flip that thing upside down, that would not be very nice.
What about the monitoring? Are there any monitors put inside so you can see what's going on?
Yeah, so there's an uplink. So like there's a bunch of sensors on everything, and that's uploading data. So you can view externally, you can view the data, but you can't give any instructions to it. There's just fixed rules of how you interact with it from like the consumer side. And we don't do any of the like steam island or like heat processing system. We just like sell like the heat as a service to any customer that will take it. So we just built the reactor.
Nice.
So I have a question, curious about funding.
Yeah.
Right? So I don't know how much it's like the US sort of venture world.
Yeah.
Do you have a small number of very interested, obviously there's probably details you don't want to talk about, but is it a small number of key investors? Is it a large number? I mean, what's
we're primarily privately funded. We have like Danish and European public grants we get also, and we sell a little bit of like products, but that's like a minority. But it is generally people who are really passionate about seeing this technology being developed that see that story and see the picture, and that's why they see sort of the upside as opposed to the risk. It's not so much like, just the standard VCs that are trying to invest.
So on that topic, isn't there a moratorium for nuclear in Denmark?
Sorry?
Isn't it like a moratorium against nuclear in Denmark?
So the Danish government has put down a rule that the government should not develop nuclear reactors.
Yeah.
But there's nothing against private industry developing it. And there's no particular rule that you in principle couldn't make like a reactor in Denmark. But there's no like nuclear approval agency. So that's, yeah. But working with it as just a reaction material, that's like well defined.
In terms of scaling up your processes, does that include all the electronics and all the components and everything that goes into it? Or will you reach a point that once you're happy with the design, that you'll look elsewhere for already developed aspects?
You mean components going in, or?
Just so you're saying that like you develop your own gaskets and the electronic systems you develop yourself, and so just how does that work for scaling up?
Yeah, we expect to build most of the stuff in the reactor ourselves and do the production ourselves and do testing on each unit ourselves. But we would really like if there's more components commercially available. Like if there's stuff out there that someone else develops, we would love to buy it and then implement it in our stuff. We just haven't seen too much available components, but yeah.
Can you talk a little bit more about why you chose the heavy water moderator and also maybe, are you guys also trying to develop your own supply chain for heavy water? Because it's not very readily available anymore, is it?
There's still a fair amount of production. There used to be European production, but that got closed down. There was in Romania, they had a bunch of can-dos there. So there doesn't seem to be any supply chain issues there, and we would love if we do not have to also do like heavy water production. But we don't, like each reactor, we need like something like 2 cubic meters of heavy water. So it's not a lot if you compare that to a can-do where they have like an ocean. So I don't think there's any limitations on heavy water production. And the thing we like about it is that you have a like non-degrading moderator. So you can do much higher power densities and you get better neutron economy. And you know, there can be like an aversion to having like something super cold next to a reactor, but I don't see it very different than like some people want to have like, you know, steam generator as their like for the coolant salt. So having water next to fuel salt, I don't see a big issue in that. That's not something I'm very worried about. But it does allow us to do a bunch of cool features that would not be possible with like graphite moderation or beryllium, for example, beryllium metal or beryllium oxide. And you, with those solid moderators, you have to cool them. Like you can, with graphite, you can use the fuel salt as a coolant, but with beryllium or beryllium oxide, you would have to have a separate cooling circuit. So you still need like a liquid going there, and then you get like swelling of the like the beryllium and stuff. So
In that region, do you use double-walled pipe and have some sort of like a break indicator in between the walls?
we have double walled, and then we have like insulation in between that's also like non-wetted, wettable, and then leak detection sensors. So in principle, like you can say if there's a catastrophic failure, then you're not gonna like, oh, shut down this leak. No, it's like a catastrophic failure. But if you have a leak, you would shut it down and you just drain the heavy water and the salt. So yeah, and even if the salt like breaks through and gets in contact with the water side, it's not going to do anything. It's just going to be cooled by the like massive flow rate of the water.
Like a scale.
Yeah.
All right. Well, we'll wrap it up here. Thank you again for a very interesting talk. Yeah, a lot of interesting things to ponder. So thank you.
Also, like at the beginning, when you're talking about the 4 terawatts,